Testing this work?
Yep.
Yes. Too loud? No, it's not. Okay. That kind of my voice. This is helpful. So when I originally signed up to do this, the concept was to do a talk on deep learning and NLP, which if you take the product of those two fields, you're going to put something that's far too large to fit into 45 minutes. So instead of doing a talk where I very briefly go over 3 contributions in deep learning in the literature from the past 3 years, I decided to dig a little further into just one particular field. And it has to be one field that I think actually, in which people have actually shown good results. Some of the other literature in deep learning and NLP, they've shown some nice results, but no one is actually using them. And that, to me, that says that they don't actually generalize. They're not actually returning something to the user. Whereas the use of neural networks and language models has actually shown some very surprising things. And so I have to come to the same conclusion. Okay, so I work here. I work at a publishing, but I work at what is a company that does not wish to be known as a publishing company because publishing is in trouble. But we have our own the Financial Times and The Economist. The company is headquartered in London. And there's also a large presence in academic publishing. Longman, as Leslie, if you've taken any graduate computer science course, as Leslie has probably been on your desktop. And in addition to that, in the education market, so I'll be very brief about this. Pearson is involved in assessments, so CSAP and things like that. Don't throw any tomatoes at me if your parents out there. So scoring things like that, designing tests of that sort, and also in some cases doing so in an automated fashion. The Boulder office where I work handles automated assessment of writing. So we do what's called automated essay scoring. Since there's only so much time, thankfully I only have so many slides, but I'll skip beyond this because it's interesting what we do. It involves machine learning. It involves machine learning and text. Just as a very brief aside, the office where I work was originally a company called Knowledge Analysis Technologies, which was founded by Tom Landauer and Peter Foltz, and one of Tom Landauer's graduate students, Daryl Latin. Tom was you could call him the creator of latent semantic analysis. His name is on the patent from Bell's board back in 1992 or something like that. He passed away just a few months ago, but he did some good work. So, if you have used machine learning in any practical way, you know that learning algorithms expect to receive some sort of structured input. Language is not fully structured. I mean, as it is, I could sit here and say things that you would understand completely that wouldn't fit into a nice grammar. I mean, approximately it would, but there's a lot of free form to it. There's a lot of improvisation. New words are being created all the time. So let's just go back to the beginning. This is something that William also did. But let's think about learning algorithms. So a learning algorithm, if you're familiar with functional programming, a learning algorithm is a function that takes some sort of training data, target variables. This is the matrix, this is a vector. It's a function that creates a function. That function, when applied to a feature attribution prediction, more or less. In fact, that applies to classification, it applies to regression. Language models, these are some sort of model of language. Hold on to your hats, we'll get there eventually. And the structure that it imposes on language is simply that language is a sequence. If you're familiar with time series analysis, that kind of modeling, it's a similar concept. You can think of it as regressing the next thing on the previous things that happened if you're familiar with time series analysis. So it's learning in joint probability like you would learn in a supervised context. But the joint probability is based strictly on the data. There's no human annotation involved in the case where you're doing, like, as you would have if you were doing classification of images. What the function, what this thing will do for you is compute the probability of a particular word given the context. So give you the probability of the next thing given what's already happened. But the interesting thing is, since it's probabilistic, it's a generative model also. It can generate text. So if you train on these models in a certain fashion on, say, all of Shakespeare, you can generate sentences that look like Shakespeare. In some cases, they're exactly Shakespeare. And that's nothing magical. This is just people have been doing that particular thing for decades. So this is what I just said. This is, so the atoms of this world, the primitives of this language are n-grams. So an n-gram is just a term, and it's just the number of things that you consider that this is the depth of the lag in the time series, so to speak. So a unigram is just looking at a particular term in a corpus and figuring out the probability of that occurring anywhere. So since you're just looking at the term itself, there's no context. Just look at this word, given all the words in the corpus, well, given the frequencies of all the words in the corpus. So this is the probability of a given word is the number of times that word occurs in the corpus divided by the number of times that any word occurs in the corpus. So it's just normalized. It's just a probability. This term is just guaranteeing that the probability, that it is a probability, that is between 0 and 1. A bigram is just n-gram with 2. So all you do is you look back one. So you're looking at the probability of a word given the fact that the word wn-1 appeared before whatever word you consider. So the cat sat on the hat, right? So to compute the bigram probability of the cat, you would first look for all occurrences of the cat in the corpus, and then you look for all occurrences of the star, anything in the corpus. But that ends up reducing to counting the number of occurrences of the. It's very simple. If you can extend this to trigrams and quadrigrams and pentagrams and so on. Everybody knows Google Instant. For some reason, I'm so old-fashioned. I was supremely annoyed when they introduced this, but it's actually kind of cool. So these are some lines from. I was a philosophy and English major, so I was an undergraduate thing. I'm kind of self-trained there, but these are 2 lines from T.S. Eliot's The Hollow Man, and it's kind of interesting. So you type in "this is the way," so you type in 5 words from one of the closing lines of the poem, and it gives you the last 2. The Lady's Ride and The Bunny Hops are both children's songs for some reason, and the third one is just the name of the last episode of Dexter. This is kind of interesting too. So I don't know what's going on, but I typed in "not with a," which it's not that common. But I guess what Google is doing, it's not that uncommon. But I think what Google is doing is they're not looking at web pages, they're looking at queries. And this is just an n-gram model over queries. So when people are at a cocktail party, they're like, who wrote that poem, not with a bang but a whimper, and they'll go and they'll type it in, or whatever, they don't do that, but something like that. So what this says is people are, when they type in "not with," they're actually more likely to be asking about the T.S. Eliot poem than kind of one of these songs like a dance song. So just in case this is new to you, I'm just going to walk through walk through this concretely, and then I'll get past this. I've got enough time. So, you go to Google, you type in, this is the way it says, return this many out of this many possible hits, and so this is the way the world, 52.75 million, this is the way the world ended, 51.2 million, and then there's some other ones, and then there's one at the end, which is 0. Yeah, oh my God. Ladies and gentlemen, this is my guy. Will Stanton. So, obvious, right? This is bigram. This isn't bigram. This is like sextagram or something. But same kind of thing is we know the counts of this is the way the world in the results returned by Google. We know the counts of this is the way the world ends returned by Google. Just divide the two and you get a probability of 0.69, which is probably what you'd expect. You did it? Yeah. Okay, so it's just, okay, great. Thank you. He's magical. So regression, classification, language models. They have different functions for computing loss or cost or something like that. With a language model, this is the geometric mean of the inverse sum, the sum of the inverse of all. So this is when you this is when you're actually evaluating a language model on a test set. So you train a language model, you want to see how well it does. If it fits the test set better, then it should give you a higher. This is called perplexity. It should give you a sort of direction. I forget, but it should give you better perplexity. And you can see here that there's an inverse probability, which suggests that, well, which means that if you were to have things that didn't occur in the training set appear in the test set, you would have a divide by 0. Okay, so you take this thing. If this is ever 0, and you invert it, you'll get an error in your computation. Same kind of thing here, right? This is just illustrating what I just described. You have something. If you have one word in your training corpus that does not appear. If you have one word in your test corpus or any text you pass through the model after you've trained it that does not appear in the vocabulary of the training set, you will have a 0 probability for that particular engram, whether it's a unigram or bigram or trigram. But the trigram and a word with 0 probability appears in that trigram, you're going to have 0 for the whole window that includes that particular term. So there are ways to address this. One is, I won't go into the details, but I just want you to know that this is possible. One way of doing it is simply to take some of the probability from the infrequent terms. So this is a high bar, and you might think, oh, these are frequent, but these are terms that occur once. So they're unlikely to occur. Let's steal a little bit from them, and then create a special token that we call unknown, or UNK. This is going to be in literature. And whenever we see a word that we've never seen before, we just allocated that probability. That way we never have any zeros. Another way of dealing with that. So the good Turing smoothing, good Turing discounting will guarantee that anytime you see a word when you're using the training model that didn't appear in the training set, you won't get a 0. That's for single terms. But if you have trained a bigram model and you see and both the first word and the second word in a particular sequence happen to be in the vocabulary either in your training set, but they don't appear in your training set in that order, that bigram will have 0 probability, so you have to deal with that. So another way of dealing with this is to do something called backup, which is you have multiple models. You train a trigram, bigram, and a unigram model, for example, and then you just take the one that has take the largest n that's actually defined, or that's not 0. Yet another way of dealing with this is to do interpolation. If you follow cable competitions, you may know that some of the winners and some of the competitions, just train a whole bunch of models, and they come up with some sort of linear recombination of them using a regression or just using, well, there's some, just using non-negative least squares or something like that. It's the same kind of idea. All you're doing is, so you know, if you have, let's just say you have 3 models. So you've got unigram, bigram, and trigram. Your alphas here will just be 1/3. It's just a simple average. But if you want to do something more sophisticated, then you have to have data to hold out for a validation set that you can use to tune these parameters. Then you can do something like what people do on Kaggle. Come up with an affine recombination of each of the models that such that the coefficients still sum to 1, just like they would if you're doing a simple average. So, any questions before? So this is basically your background, your very quick background on language models. Now, I'm going to step over to the world of deep learning and talk about some neural networks that do this kind of thing, but they do it in a much cooler way than just counting and dividing. Some questions? Okay. So, I did think at one point of titling my talk, Deep Learning Isn't, which is to some extent true when it comes to language, when it comes to neural network language models, because the very first one was not deep at all. It was basically just a 2-layer network, and one hidden layer network. But it was just, but it was very clever. So it was done by, so you know, there are 4 people in the world who know deep learning. 3 of them work for big web properties. One of them works for the University of Montreal. It's Joshua Bengio. He's the only holdout. Not going to Facebook, Google, or Baidu.
Not yet.
Not. Well, he said that he's adamantly against it because he wants to do AI research and not try to have people.
Things they can do with money.
Place a lot better. Yeah, that's true. But apparently he's getting grants. He's got a lot more students. Okay, so onward. So this is the and now magic occurs slide. The cool thing about neural network language models is that not only do they give you a language model, so not only do they give you a function such that when you apply that function to a sequence, it'll give you a probability of the sequence, or a probability of the last word in the sequence given the context. But they also learn distributed representations for the words. So distributed representation, this is, in neural network terminology and in NLP to some extent too, there's this notion of distributional semantics. So, and all that means is basically you represent words as vectors. That's all that's going on. So, learning word representations just means that for every word in your vocabulary, every word that appears in your training set, you end up with some number of real values. That's it. What they allow you to do is do cosine similarity, to see how similar two words are. They allow you to do certain algebraic cool things that I'll show you that are surprising. I'm not sure how far they'll fit in. I'm not sure how far you can go with them, but those results were published last summer, and were the reason why Tomas Mikolov, we'll talk about some of his work in just a second, was immediately moved from Microsoft Research to Google. They snapped him up like very, very quickly. I mean, I think his paper was published, it said Microsoft Research on it. He was already Google.
Yep.
Okay, so I'll start it off. So just a neural network, forget the dashed lines, it just complicates things too much. So the inputs to the network, let's say we have okay. So let's say we have a bigram language model. That's what we're trying to train. Then all we do is get rid of these two. Get rid of these with the dots, just to keep it simple. C is a matrix, and that matrix is supposed to ultimately, once the model has been trained, contain these awesome distributed word representations. But initially, it just contains random values. Random, normal, standard deviation, whatever. I don't know exactly how I describe it. I mean, sometimes they try to be a little closer to zero, so if they random, normal, standard deviation, it doesn't really matter. So you can see here that so this matrix contains these representations. When you subscript that matrix by WT minus 1 representations, give me the vector for the word that appeared before the current word, or the word whose probability I'm trying to estimate. So when while training this model, that word is looked up from the dictionary, from C, from this matrix. And the values, the distributed representation of that word is populated, where this input is populated with those values, whatever they happen to be. But in the first pass through, it's going to be random. Then apply element-wise hyperbolic tangent, which is similar to sigmoid logistic. And then you apply a softmax, which just gives you a probability distribution over basically all of the terms in the dictionary. So say you have 100,000 words in 100,000 unique words in your training set. What you're trying to train this model to do is output a vector such that the word that you're trying to predict is the word whose probability you're trying to estimate has the greatest value in this probability distribution. So let's say, let's say 100,000, you have 100,000, that'll mean that the output vector for this model is 100,000 elements. And they're reals, but they're all basically in the range 0, 1. Most of them are going to be, most of them should be very, very close to 0, but you're going to have some that are a little greater than others. So we have 10 minutes left. So that propagation practically happens. Everything's great. What happens is when the error signal is back propagated through to here, this value is updated in the matrix. So repeatedly, words are grabbed. They're grabbed from the dictionary. They're grabbed from the string from C, this matrix, plopped in the slots, just plopped into there. Forward propagation, back propagation. Weights are updated. Eventually, it converges. Now that's circa 2003. Fast forward to 2010, and you have Tomas Mikolov and some colleagues doing the same kind of thing with a recurrent neural network. Now, the output here is basically the same thing. They're doing it. This is just straight out of paper. So the output layer is softmax, so it's giving you a probability distribution over your 100,000 words, something like that. The input here is, if you read the literature, they'll talk about one-hot vectors or one-event vectors. And so basically, if you have 100,000 words in your dictionary, they're all, so the input, the word, the element I is going to be 1, everything else will be 0. One big vector. And then there's a recurrent layer in the middle. This was interesting. I think this is part of his dissertation work. It was, I think, a bit faster than Bengio's model, but it wasn't until, okay, well, there's only so much time left, so I'm going to take my word for it. This is training set results, so you have to take it with a grain of salt, but basically, you can see here, so Canyon 5, this is Kessler May 5, it's a best-in-class non-neural language model, plus the recurrent neural network typically gives you better perplexity across the board, the similar training set sizes. Now this is just an 8-line recombination, so I think they're holding out some data for validation or student parameters, or like you'll see in some academic papers, they were just hacking network fitting. Sorry, black humor. So, okay. Now, last year, this model is really no different from the one that was in the 2010 paper. What is interesting about this, however, is that two of his colleagues at Microsoft started to look at I don't know if they do this on priori, but they started to look at the column vectors of this weight matrix U, and they started to think about them as learning word representations. So in the Bengio model from 2003, you had a matrix and you held off to the sign, and then you just fed those vectors into the model, and then fed their updated versions back into the model after that propagation. Here, the word representations are in line, so they're part of the weights of the model themselves. The weights of the model itself, right there. So if you're familiar with weight semantic analysis, or I think people use LDA, weight tertiary allocation, or topic models. I've never used topic models. I've never used LDA because I have a job to do in LSA, and it works very well for it. But what you know from if you're experienced with those is that when you compare those vectors, things that are similar tend to be made more similar when the model has been trained. Even if they're not obviously similar, things that are dissimilar tend to go. It's kind of like an energy model. Pushes the right things together and pushes the wrong things apart. So you can learn a similarity structure. If you're doing LSA, the similarity structure you're learning is completely unsupervised, except for the parameter, except for basically the dimension, the chosen reduced dimensionality that you have for K. So with LSA, 300 works best for what we do. And that's something that you have to choose. You have to tune that parameter by some mechanism above. People do whatever they have to with natural language tasks. So, not only can what's really interesting, and this really took a lot of people by surprise, is that the vectors that were learned in the recurrent neural network in the column vectors from the U matrix have these really cool algebraic-like properties. So this is a pretty simple example. So if you look at the relationship between the vector you get by subtracting man from woman, or subtracting aunt from uncle, subtracting uncle from aunt, or subtracting king from queen, they are basically the same. I mean, in some cases they'll do PCA to reduce it down to 2 dimensions so you can actually visualize it. But they tend to be very close, surprisingly close. Now, to give you a sense, so that's these male-female relationships, right? Here is sort of plurality and sex. So the way they're actually testing this is they take, say, so take the vector for kings, subtract the vector for king, add the vector for queen, and then they search the neighborhood using cosine similarity. And the first one that comes up, the closest one, is the one that they choose when they're evaluating these representations for the miraculousness. Now, using the test set that they had, which they created themselves for this paper, and comparing the performance of their model to LSA, which doesn't pay attention to order. They were getting, their accuracy was something like 25%, which is pretty damn good, considering what they're actually doing. When you think about that, this is not, so people see this and they wonder, well, how are you actually arriving at this? So when Nicola went to Google, they released some papers, and they mostly sped things up. And then there's been one paper that came out last week with Nicola and someone at Stanford that was basically about taking these word representations and trying, well, not necessarily taking these word representations, but training models so that you can represent paragraphs. And that was a disappointing paper to read because they didn't compare. I don't mean to sound like a broken record. I don't mean to sound like a shill. But we use LSA, and LSA happens to be very effective. And they didn't compare to LSA at all. Now LSA was created back in 1992. It should be a reasonable baseline. It should be comparing to something like that instead of comparing to TF-IDF. Especially when you're dealing with very short phrases. That's the only thing it's a very criticism to make. But this is still very amazing. What I think would be very nice to see in the future is more investigation about how much information is really encoded in the embedding space. That's what's really going on here is, so with LSA or something like that, you're doing an embedding space that gives you similarity. And it gives you what you expect to be reasonable similarity. But this is encoding things, encoding the words in a way that some other information is actually present in the space itself. I don't know how many dimensions they're using. I think maybe 100, 200, something like that. So you have this 200-dimensional space that's actually capturing some of this information. That's really cool. It's very, very cool. Now, in practical terms, people use language modeling to do things like author identification. I think one of the anonymous authors of the Hegel's papers was identified by I don't know if it was a linguist or something like that. So we're not practical application, but there's some very, very cool cutting-edge things going on with them right now. So if you'd like to try it for yourself, in 2013, after he went to Google, Nicola, and a couple of early top people there, Jeff Dean was on the paper. They took his recurrent language model and they made it just insanely fast. You can train with a corpus of 1 billion words or more on a workstation in a day. I mean, it's just like, it's ridiculous. It's great, but it's unbelievable what you can get done there. You can get the code yourself. You can try it on whatever corpus you'd like to. It gives you nice similarity structures. There's a Python wrapper for it, which is actually, so the Python wrapper is in a Python package called GenSim, which I think has topic models as well. And there's a link in my slides, which I can make available on the website to an online demo. So I think that is it on with 5 seconds over here. I'm sorry. Any questions?
So you work with automated essay scoring. So how would you apply the output of this algorithm to that?
I think this isn't so. Some of this stuff is proprietary, right? but it's patented. So I believe I wouldn't be giving away too much. It just said, well, try imagining combining a k-units neighborhood classifier or regressor with these representations. So if you have an essay if you have an essay that's on topic, with respect to a prompt, write why was Abraham Lincoln great? Some kid writes about Ferraris, right? So that's not a great example, but something like LSA, something that finds a nice distributed representation of a document will be able to tell you practically whether something is appropriate to a particular question. And you can also, that's a negative way of looking at it, in the sense that what you're trying to do are find things that shouldn't be given to its tools. Another way of looking at it is if one essay happens to be near in this vector space to essays that are have a high score, then that essay should have a high score. I think that's all I'd say.
And so I'm a little curious about the Dronen package for Python. Is the neural network for this kind of language model available in that package or not?
Do you know Pip?
What?
Pip?
Pip. Oh, no.
If you have Python, if you have a new Python, just type pip install Dronen. And it does everything. I believe it allows you to train everything. I haven't used.
Okay, I've used the Dronen myself, but my question is whether neural network is available in Dronen or not.
So this one. Oh yeah, right. So basically, this paper, I don't. So one thing I haven't done with the implementation of Word to that, which is C code. So one thing I don't know is the way people do some machine learning papers is to say, well, here's a problem, and here's how we're thinking about theoretically. If we might be thinking about theoretically, there's no that really makes sense. But we really want to cast it into a slightly different form so we can train things much faster. And I don't know if it may be that there is that, and if that's the case, well, okay, let me put it this way. Jensen is not a general purpose library for neural networks. If you want to tinker, you've got PyLearn 2, which is very good. And you also have, I think, PyBrain is another Python library that supports neural networks and supports stacking and so on. Although it tends to have, I think, and it's oriented a bit towards the reinforcement learning community where they're doing robotics and that sort of thing.
So you mean that if I want to try neural network with some for some language model, the correct step is first use Dronen to transform your word to vector in the vector space or whatever stuff you use, and then you train the neural network model on that vectors.
Okay, right. So do you have labels in the scenario? You have text, right?
Mm-hmm.
And you
we have a label.
You have labels. That seems like a reasonable thing to do.
Okay.
Yes.
So for that paper you're talking about, their 200-dimensional space. How are those dimensions defined? Do you know?
Can you elaborate on that question? So,
well, for example, in your example, there are 2 dimensions that I can see.
Oh, right. So okay. So the question was, how are the dimensions in this? I don't remember the exact number, but it's a 200-dimensional space in this paper. How are those dimensions defined? And the comment to follow up on that was that all we see here are 2 dimensions. So these 2 dimensions, this is just for purposes of illustration. Now in the 200-dimensional space, you can take a vector, subtract another vector, add another vector, and do cosine.
Yeah,
that's all they're doing.
I understand.
Okay.
The question is,
what's the embedding?
Yes.
What are the semantics of dimensions?
Where did the embedding come from?
Yes.
The embedding is learned by back propagation.
Okay, so it's completely learned.
Yes.
That was the question.
Okay, yeah. Good, yes.
Does that eliminate the need for stemming? Like for stemming of text?
Okay, so I don't know. I mean, you would think that I don't know. I honestly don't know. It's a good question.
So I'm trying to understand this picture. So in LSA, right, your similarity between documents is the relationships are defined kind of geometrically,
Yeah.
right? So in this case, are you saying that it's not exactly just a geometric relationship. There's also some sort of this algebraic graphical relationship. So that's the
Yes.
advantage. Okay.
Yeah, I mean, so you know, what you get from LSA is what you get from doing SVD, which is a generalization of what you get from the TCA, which is just doing a least squares fit, right? That's all that's going on there. This is doing something different, which is cool. Yeah.
But that's still like the word level representation, right? If we're doing sentence level representation, vanilla LSA always had trouble with man bites dog versus dog bites man. This is, I assume, is going to have the same kind of similarity issues.
Okay, so the way I look at it, because of the word representation learned by this model, those representations are informed by those kinds of syntactic relationships. But I haven't seen any work that implies that. I mean, okay. So when I saw this, I started thinking, well, what I would really like is a way to, what you need in order to make this supremely awesome is some sort of universal algebra language that says when you start with the, and this is what you do with the next thing, but it implies maybe having a parse tree. Okay, and I would love to work on that, but Pearson doesn't allow me to. Because basically, I think doing that requires 10 engineers at Google working for 2 or 3 years. In order to really find, to really explore that space, you need unlimited time and attention. You need people thinking about this on the weekend. So it's a great question. And that's, anyone who looked at this has an intuition about what's happening here thinks the same thing. So, time to do it?
Thank you, Nick. Next month, we will be back in Denver. We have a great presentation on field programmable gate arrays and GPUs for data streaming. Wednesday, June 25th. So I hope to see you there. Please join us at Old Chicago and have a wonderful evening.